Welcome back, everyone. Hope you all had a good weekend. So last time we talked about the bias variance trade-off. Basically, this is a theoretical analysis of overfitting and underfitting. And basically the main result is that we have expected error equals bias squared plus variance plus irreducible error. And basically, irreducible error could not really, we can't really do much about that. That's just the noise from the data generation process. But in order to have a good model, meaning good or low expected error, we needed both the bias and the variance to be small. We looked at this again by revisiting the example from the Colab notebook. Afterwards, we talked a little bit about optimization motivated by nonlinear least squares. And then we realized that, okay, now actually there's no way for us to obtain an analytical solution to the optimal parameters. So we introduced an iterative optimization algorithm called gradient descent. So today we're going to continue talking about optimization and the different optimization methods. So just to recap a little bit, in gradient descent, we choose some random vector to be the initial set of parameters called theta 0, where the superscript denotes the iteration number. Then we go through many iterations of the parameter updates, each time taking the previous parameter estimate, subtract a learning rate or step size times the gradient evaluated at the previous parameters. Once we have exceeded the maximum number of iterations, or if the algorithm has converged, then we return the parameter. And this is what it looks like on a convex example. So for example, let's say theta 0 is up here. The gradient is the direction of steepest ascent. So when we subtract gamma times the gradient, we're going in the direction of steepest descent. So that's this direction. And then we keep doing this until the algorithm has converged. And hopefully when that happens, we're actually at a local or better yet, global minimum. However, this is not always guaranteed. If we pick a step size too large, we can either oscillate quite a bit, taking too many iterations to converge. So that would be this example. So here we're still going down the direction of the gradient, but this gamma t, the step size, is too large. So we overshoot the minimum point and we go to the other side. And then each time we overshoot. In this example, eventually we still get to the bottom, but sometimes if you have a step size that is way too large, you could actually diverge. So that means that your parameters go off to infinity. This is the example where the step size is just right, as we have seen on the last slide. And then there could also be examples where the step size is too small. So we never really make enough progress to converge to the local minimum. Global minimum in this case. So, and then we kind of talked about what convergence really means, and there are two different notions. The first notion of convergence is basically as the iteration number increases, the objective value gets closer and closer to the target objective value, usually the minimum. Or we could talk about convergence to a target parameter vector. That means that our theta gets closer and closer to some theta star. Usually we don't really know what the best objective is and what the best parameter is. In fact, we're trying to find them. So then we have to use a proxy to detect convergence. So typically what we do is we simply compare theta t with theta t minus 1, and if the change is very small, then we say the algorithm has converged. Alternatively, we could look at the value of L evaluated at theta t minus 1, compare that with L evaluated at theta t. And if the difference is very small, we also could say that the algorithm has converged. Okay, So it turns out that there are some theoretical guarantees of convergence for gradient descent. So roughly speaking, if the objective function, so that's the L function, is convex and C Lipschitz, then gradient descent with a small enough step size is actually guaranteed to converge to the minimal objective value. Okay, so remember that C Lipschitz means that for any two inputs to the L function, the difference between the result of evaluating these 2 points on L is always less than or equal to C times the distance between the 2 points that we did the evaluation on. If the L function is everywhere differentiable, then this condition can be simplified to the norm of the gradient of L is always less than or equal to C everywhere. So this is kind of illustrated by this picture here. So here in the purple, we have a differentiable function. And then these two lines, these two straight lines, have a slope of plus and minus C. So because the purple function, as we move along the purple function is always above the lower minus C, the minus C slope line, and below the plus C sloped line. This shows that the gradient, or in this case the derivative, is always less than or equal to C. So the purple function is a C Lipschitz function. So hopefully you remember what C Lipschitz means. Okay, and then the other condition is that the function must be convex, right? So again, a convex function means that if you draw a line between any 2 points on the function, then the line is always above or equal to the function itself. Okay, so on or above the surface. And if the function is everywhere twice differentiable, then it is convex if and only if the Hessian is positive semi-definite. Okay, so for the guarantee of convergence of gradient descent, we need the function to be convex and C Lipschitz. And furthermore, we can actually even say how fast the algorithm converges. So this is kind of quantified by these two paragraphs here. So the gap between the minimum objective value and the objective value at iteration t is at most big theta of 1 over root t. So as you have more and more iterations, the difference between the current objective value and the optimal objective value is kind of falling or is reducing at 1 over root t. Equivalently, if we want the parameter vector to have an objective value that is epsilon larger than the minimal objective value, then we need big theta of 1 over epsilon squared iterations. So basically, to get half the error, we will need 4 times the number of iterations. To get 4 times the error, we need to have 16 times more iterations. So that's what that means. Okay, so that's the theoretical guarantee of convergence. So actually we do need some assumptions here. The objective function must be convex in C Lipschitz, and also the gradient descent must be done with a sufficiently small step size. Okay, so what happens when the function is not convex? So we can take a look at 2 examples. So on the left, this is a non-convex function. We can see that if we draw a line, let's say connecting these 2 points, that line is actually not above or on the function. In this case, if we do gradient descent, so again, we're going to go down the direction of steepest descent, but in this time, the parameter value actually gets stuck somewhere over here, which is not the minimum. The minimum is somewhere over here. So on the right side, we actually have an example where the function only has 1 local minimum, and also the local minimum is indeed a global minimum. However, the function is not convex. We can see that by drawing a line from my cursor here to somewhere here. So if you draw a line like this, you can see that the line is actually not above the function. In this case, if we run gradient descent, because the surrounding area is very, very flat, we could have actually very slow convergence. It takes many iterations to travel very slowly in the flat area before we get into kind of the really deep part of the function. So these are two examples of what would happen if you run gradient descent on non-convex functions. So there are no guarantees for kind of convergence to begin with, and even if the algorithm eventually converges, there may not be a guarantee on the convergence rate. Okay, let's move on and look at more examples. So here we have a function f of xy equals to absolute value of x to the power of 0.8 plus y plus 3 squared over 15. So if you take the gradient, you get that the gradient of f is equal to sine of x times 0.8 over x, absolute value of x to the power of 0.2. Actually, so here we're only taking the partial derivative of f with respect to one of the variables x. But basically, because we have because we have an absolute value of x in the denominator, when x goes to 0, the partial derivative of f with respect to x actually goes to infinity. So x equals to 0 is over here. And when we get to this place, it turns out that the magnitude of the gradient becomes infinity. So that means when we do gradient descent, so if you just go back to the gradient descent algorithm, we need to subtract gamma t times the gradient, right? In the previous case, one of the components of the gradient approaches infinity as we approach x equals to 0. And that actually happens to be the global minimum, actually. So in this case, we're going to subtract a number times something that is infinitely large. So this causes some unstable changes in the parameter values. So here we have the global minimum. If we try gradient descent, we can get kind of closer and closer to the bottom, but at the same time, our gradient component goes to infinity. So then at some point, it kind of jumps out suddenly. Okay, so here we have divergence due to exploding gradients. Exploding gradients is a common term for when the gradient goes to infinity. Previously, we had vanishing gradients, also a very common thing that happens in machine learning. Vanishing gradients means the gradient is very close to 0. Here we have exploding gradients, so this is a top-down view. So basically, it's really hard to settle to the bottom here. As soon as you settle close enough to the bottom, the gradient goes to infinity and then you come right back out. So let's just take a look at this one more time. Yeah, so it jumps out here and then it goes back. But then when it goes back, eventually it's going to jump out again. Okay. So these three examples were non-convex functions. Actually, yeah, I don't believe this function is convex either, but you can also imagine there could be a convex function where maybe you have some exploding gradients near the minimum. So sometimes even for convex functions, you could have this behavior, very slow convergence. So one example of a convex function with a very slow convergence is actually this one. This is f of xy equals to 4x squared plus y plus 3 squared over 15. Okay, so this is actually this is basically a paraboloid. So it's basically a parabola in 2 dimensions. In the x direction, so if you go along the x direction, we have a parabola that looks like 4x squared. In the y direction, we have a parabola that looks like y squared over 15 because it's over 15. It's actually very shallow. The curvature is very shallow. Okay, the plus 3 is just the translation. Whenever we have a quadratic function, we know that the Hessian is simply going to be, you can work this out yourself, but when we have a simple quadratic function like this, the Hessian will simply be the coefficients on the squared terms. So that's going to be 4. Actually, the 2 will come down when you take the gradient. So you get 8 over here, and then you have 2 over 15 over here. Because this is a parabola centered at 0 and minus 3, we know that 0 minus 3 is the optimal parameter vector. But gradient descent will actually converge very slowly because in one direction, in the x direction, there's a lot of, the gradient is pretty large compared to the gradient in the y direction. So gradient descent will go down the x direction very quickly. It moves to the middle of the x parabola, but then the y parabola is very shallow, so then it still takes many iterations to converge to the minimum, which is somewhere actually over here, 0 minus 3. So the parameter actually converges very slowly, but once we get to the middle in the x direction, the objective value is actually very close to the minimum just because in the y direction the function is pretty flat. So even though the parameter converges slowly, the objective value converges quickly. Okay, let's review a little bit about gradient descent. So which of the following statements about gradient descent is true? So take a couple of minutes to think about all of this. Okay, let's take a look. So first, gradient descent may not find the global minimum on non-convex functions. Okay, definitely true. So we saw some examples. These are some examples of non-convex functions, especially this one. Gradient descent may not be able to find the global minimum. Okay, so just looking for the slide. Okay. Next, gradient descent may diverge on non-Lipschitz functions. Also true, that was the same slide that we just looked at. Well, actually the next one. This one is a non-Lipschitz function because the gradient goes to infinity, so then gradient descent may diverge. Okay, C. With a sufficiently small step size, gradient descent always converges at a rate of big theta of 1 over epsilon squared to the minimal objective value on convex non-Lipschitz functions. So it's a bit of a mouthful, but we do have all the key conditions. So a sufficiently small step size, convergence rate is 1 over theta of 1 over epsilon squared. That's what we have seen, and that applies to convex and Lipschitz functions. Okay, and the convergence is actually to the minimal objective value, right? So this one is true. So that's basically all the information we had on this slide. Right, so convex, C Lipschitz, and then convergence to minimal objective value. Okay, next, with a sufficiently small step size, gradient descent always converges at a rate of big theta of 1 over epsilon squared to the minimal objective value on functions whose every local minimum is a global minimum. So this looks like exactly the same as C. The only difference is that for C, we have convex Lipschitz functions. For D, we have functions whose every local minimum is a global minimum. So are they the same? So it turns out that that's not the same. Even if a function has every local minimum being a global minimum, the function still may not be convex. And we actually saw an example of this on this slide. So this function only has one local minimum, and that local minimum is a global minimum as well. But this function is actually not convex. So because the function is not convex, there are no guarantees on the convergence rate of big theta of 1 over epsilon squared. Okay, and last one, E. With a sufficiently small step size, gradient descent always converges at a rate of big theta of 1 over epsilon squared to the optimal parameters when the objective function is both convex and Lipschitz. Okay, so now the function part is the same as C, but C says convergence to the minimal objective value, whereas E is saying convergence to the optimal parameters. Okay, so actually it turns out that this is false because the convergence guarantee was actually on convergence to the minimal objective value. And we also saw one example where the function is actually convex and Lipschitz, but convergence to the optimal parameter value was very, very slow. But convergence to the convergence to the optimal parameter is very slow, but convergence to the minimal objective value is pretty fast. Okay, so that was the in-class review. Hopefully you got all of these. Okay, so next we're going to look at some more advanced iterative gradient-based optimization methods. So the next one we're going to look at is gradient descent with momentum. So a lot of times people just call this momentum. Some people would also call this Polyak's heavy ball method. So let's just go over the algorithm. So the way to think about this algorithm is to think of theta as kind of representing the position of the particle that is moving around on the surface. And then there's a variable delta theta. This is kind of, think of this as the velocity of the particle. If we jump down to this line, you can see that the next position is the previous position plus the velocity. right? So this is kind of like a velocity, right? Okay, so now there's another line that computes the velocity, what the velocity should be. And the velocity is basically going to be a number times the previous velocity minus gamma times the gradient of L evaluated at the previous point. So basically, the gradient is causing a change in the velocity. So the gradient is kind of like acceleration, right? So the gradient is causing acceleration, changing the velocity, and then whatever velocity we have, that changes the position of theta. Okay, and then we keep doing this many iterations until convergence. And hopefully we can do a little bit better in some cases compared to vanilla gradient descent. So here, because we have momentum, you can kind of see that, first of all, we're overshooting a little bit in the x direction. However, in the y direction, because we're picking up, because the y gradient is consistently in the direction to the right, it's causing more and more velocity as the iteration number goes on. So eventually we're actually able to move a considerable distance in the y direction until we get to the minimum here. So now maybe you have noticed that previously we had one hyperparameter, gamma t, but now we have another hyperparameter, alpha, which is between 0 and 1. So this is called the momentum parameter. So we have the momentum parameter and the step size or learning rate. So alpha basically controls how much of the previous velocity do we keep. Okay, so that's momentum, and let's do a side-by-side comparison between momentum and gradient descent. So this is a gradient descent. Actually, if we set gradient descent, if we look at momentum and set the momentum parameter alpha to be 0, then we would always have delta theta equals to minus gamma t gradient of L, right? So that actually turns out to be exactly the same as gradient descent. So gradient descent is basically momentum with alpha equals to 0. More generally, in momentum, the gradient changes the velocity, and in gradient descent, the gradient directly changes the position. Okay, so let's compare them in a picture. On the left, we have the picture we saw before, where gradient descent gets stuck in the higher local minimum over here because we could not get over this bump. Momentum is kind of, as we go down the gradient over here, we're keeping some of the previous velocity because the gradient that goes backwards to the right here was not sufficient to reduce the velocity to 0 and then go backwards. So that's why momentum sometimes could actually get over this bump, and eventually our parameter settles down at a lower local minimum. This is actually not guaranteed. In this example, this is what we see. Sometimes this doesn't happen, especially if we don't have the right step size, for example. So in the second case, I'm using a smaller step size. So momentum goes down this way, but then because the step size is smaller, it doesn't actually get over the bump and it actually turns around back to the higher local minimum. Okay, another example that we saw earlier. So this was the example where we had one local minimum, which is also the global minimum. However, this function is not convex, and there's a kind of a really flat region where we have vanishing gradients. So with regular gradient descent, very slow because of vanishing gradients, but momentum, because the gradient is consistent in one direction, i.e. towards the center, momentum is able to pick up speed and then get to the bottom much faster, even though the gradients here are very small, right? Because we're accumulating we're accumulating speed by having acceleration. Again, this is just a picture that we see where momentum is kind of working, but it doesn't always work. For example, if the step size of momentum is too small, we may have the same situation over here, just not enough progress towards the middle. If the momentum algorithm uses a step size that is too large, by the time you get to the middle, you may have collected too much speed, and then you would overshoot where the bottom is, and then you come back up. So basically, momentum to work better, you still need to find the right hyperparameter, the right momentum parameter and step size. Okay. So finally, we're going to take a look at the non-Lipschitz example again. So again, with the gradient descent, it was diverging just because as we get to the optimal point, where x and y are both, actually x is 0 and y is -3, that's the optimal point. When we get to the very center, the x component of the gradient diverges, so then gradient suddenly jumps out. With momentum, actually it still diverges because at the bottom we're still dealing with infinite gradient, but it doesn't diverge as badly, meaning that it doesn't suddenly jump way out. And that's because we're keeping some of the previous velocity. So one very large gradient, especially if you're not exactly at the very middle, that has a less of an effect just because we're still keeping some of the previous speed, which is not infinity. Okay, so it seems like at least with momentum for these two examples, if you pick the right hyperparameters, so hyperparameters are basically anything that affects the optimization algorithm, but are not actually the parameters themselves. So for momentum, we have alpha, the momentum parameter, as well as the step size. So these are the hyperparameters. With the right hyperparameters, momentum sometimes can resolve some non-convex issues. Here's the other example. But with the non-Lipschitz function, it seems like even momentum is not able to do much better. So how do you get around non-Lipschitzness? A lot of times we can try to find a strictly increasing function to apply to the objective function. This is kind of similar to how when we're doing maximum likelihood, we could apply the log function, which is strictly increasing, to the objective, which was the likelihood function, and then that actually doesn't change where the minimum or the maximum occurs. So for example, if we want to solve the problem of minimizing over W for some 2 norm, well, the 2 norm is actually has a square root, and with a square root, you actually have a non-Lipschitz point, like a non-differentiable point at the very middle. So if we apply the squared function, we can actually remove the square root, and then that actually doesn't change the the W that minimizes the objective. Okay, so instead of solving this, we're actually going to solve min over W of this 2 norm squared. Okay. Another way of getting around non-Lipschitzness is to do gradient clipping. So there's not really any theoretical justification, but this is actually pretty common and works pretty well in practice. So instead of using the gradient, instead of directly using the gradient over here, we're actually going to use a kind of a complicated expression, but it's actually not that complicated. So let's just take a look at this expression over here, break it down, what it means. Okay. So normally we would just simply calculate the gradient of L. So this is actually the ith partial derivative of the gradient evaluated at a certain parameter. So the parameter at iteration t should be superscript. So this is actually min of the same thing, but then absolute value with some number. So this number we can choose. Okay, and then times sine of the gradient component. Okay, and then we do this for all I in 1 all the way to n, so every component. Okay, so what exactly does that mean? So first, sine of a variable is just equal to 1 if x is greater than or equal to 0, and then minus 1 if x is less than 0. Okay, so probably many of you know this, but just wanted to make sure. Okay, so what are we really doing here? So we're going to look at the absolute value of each component of the gradient. So whenever you have a min, you basically have cases, right? So if the first part is smaller than the second part, then basically we're going to take the first part as part of out of the minimum, and then times sine of the same thing. So this is if the first part is smaller. Okay, smaller than 10 to the power of 3 or whatever you want to choose for the number here. And it's going to equal to 10 to the power of 3 times sine of the gradient, otherwise. Okay, so I'm just looking at the two cases for the minimum. For the first case, if you take the absolute value of something and then you multiply it by the sine of that thing, well, absolute value will keep your function, will keep x positive if it's already positive, so no changes if x is positive, and the sine is always equal to 1. So if x is positive, then we just get x. If x is negative, then the absolute value of x would be equal to negative x. Negative x times minus 1 will give you x. So this is always equal to x. So if you take the absolute value of something times its sine, you always get back the original thing. So this first case is actually nothing other than the gradient, the ith component of the gradient. So we use this if the absolute value of this component is less than some threshold. And then otherwise, if the absolute value of the gradient component is bigger than the threshold, we're simply just going to use that threshold, the value of that threshold, in place of the gradient. Of course, we still want to move in the same direction as the gradient, so that's what the sine is doing. Okay, so just wanted to go through that slowly in case you haven't seen something like this before. So basically use the gradient if the magnitude, so for every component of the gradient, we should use the value of that component if it doesn't exceed this threshold. If it exceeds that threshold, we're going to cut it off and use that threshold, but then keeping the direction in that component. So this, again, no theoretical justification, but sometimes it works well in practice. Okay, so let's move on to another optimization algorithm. So we're going to start with gradient descent with momentum. So remember that theta is the position, delta theta is the velocity, and then the gradient over here will change the velocity. Nesterov's accelerated gradient is actually almost exactly the same. We have position, velocity, and then the gradient is appearing here and is changing the velocity. The only difference is what we're plugging in into the gradient. So here we're plugging in the previous parameter, and over here we're plugging in the previous parameter plus alpha times delta theta. Okay, so let's just take a look at what that looks like just with a simple drawing. Just gonna draw some function, and then I guess this can be theta, and then normally we pick some theta theta of t minus 1. Let's just do theta 0 actually. One second. Okay, that's unfortunate. This Okay, somehow it's just erasing my theta and the function at the same time. It's okay. So we have our theta 0. So initially, delta theta is equal to, so we don't need the vector in this case because theta is just a scalar. Initially, delta theta is 0. So the gradient is actually pointing in this direction. So we're gonna move some direction. We're gonna move some amount in that direction in the first iteration. Okay, so delta theta is 0. So that's 0. So delta theta initially is just going to be step size times the gradient, evaluated at the previous theta, right? Our previous theta was here. So then theta 1 would be here. Okay, so next so now we have some delta theta, some other delta theta, right? So delta theta, it's probably going to be some minus, it will be some negative number basically. So there's already some, so delta theta is really represented by this arrow here. Okay, so now going back to the algorithm, in momentum, we're going to keep some of the delta theta and then subtract the gradient again, but then the gradient will be evaluated over at the current or at the previous the previous theta. So momentum will keep this arrow, the size of the arrow, and then it's going to look at the gradient over here, which is, I guess, it's pretty close to 0, and then modify the arrow based on how big the gradient is. So because the gradient is pretty flat here, maybe we'll get to here, theta 2. So this is for momentum. But for Nesterov's accelerated gradient, we're going to evaluate the gradient at theta t plus t minus 1 plus alpha delta theta. So what that means is that instead of evaluating the gradient at this point, at this point, we're going to evaluate the gradient at delta theta, which is this. We're going to evaluate the gradient at this point plus alpha, some number, times delta theta. So we're going to evaluate the gradient over here, which is going to be a little steeper. So in this case, probably Nesterov's gradient will kind of take this point all the way to somewhere a little farther along. So that's why it's kind of called the accelerated gradient. So this is theta 2 for Nesterov's accelerated gradient. So it's looking ahead, when it's evaluating the gradient, it's looking ahead at, is evaluating the gradient at the point that is ahead of the current point. The current point is theta t minus 1, is going to add alpha times delta theta to this point and then evaluate the gradient. So it's evaluating the gradient at somewhere down the road, somewhere maybe roughly speaking 1 step ahead. Okay, so this is basically some kind of look ahead. You can think of this as accounting for the inertia. If you already have some momentum kind of going down some function, why evaluate your gradient at the beginning point? Why not? So what Nesterov's accelerated gradient is doing is evaluating the gradient somewhere ahead because it knows that you're going down that direction anyway. So it's accounting for the inertia. Again, it's not really very precise physically, but that's the intuition. Nesterov's accelerated gradient accounts for the inertia when computing the gradient. Okay, so I think that's a pretty good place to take a 10-minute break. So we'll be back in 10 minutes to cover adaptive gradient methods. Okay, welcome back. So let's now move on to adaptive gradient methods. So we're going to motivate this by looking at the previous function that we saw, 4x squared plus y plus 3 squared over 15. We know this function is a paraboloid it's actually a positive definite function. The main problem with gradient descent in this case is that in one direction, the function has a pretty sizable gradient compared to the other direction. So this is actually the reason why the algorithm converged very slowly to the optimal parameters. The underlying reason was actually that the Hessian matrix has very, very different magnitudes in the different components. Okay, so the eigenvalues of the Hessian have very different magnitudes. So, but actually, this shouldn't really happen because the only reason that happens is because of these scaling factors, right? So can we just redefine another coordinate system where in the new coordinate system, we don't really have the problem of really different Hessian eigenvalues, i.e. really different coefficients here. So to do that, we're going to let x prime equals 2x and y prime equals root 15. And then we're going to write the function f of xy in terms of x prime and y prime. So let's do that. Okay, so now I guess we're using green color. So f of x equals 4x squared plus y plus 3 squared over 15. And then we want to write f in terms of x prime and y prime, where x prime is equal to 2x, 2 because it's the square root of 4, and then y prime equals y over root 15. Okay, so then we want to change this whole thing in terms of x prime and y prime. So that means we can rearrange the equation for x and y. Y prime equals y root 15. Okay. So now we can plug things in. So f of xy will become 4 times x prime over 2 squared plus y prime. Did I make a mistake here? Yeah, it looks like I did. So here y should be equal to y prime root 15. Plus 3 squared over 15, right? So we can kind of simplify this a little bit. And then you will see that the coefficients will cancel out. So the x1 is the 4x prime squared. That just becomes x prime squared. Plus, over here we have, so we have y prime squared. What's the best way of doing this? I think the best way of doing this is factor out the root 15. Yeah, so let's factor out the root 15. So we have root 15y plus 3 over root 15. And then all of that is being squared. And then we divide by 15. So this is equal to x prime squared plus 15. So root 15 squared is 15. Y prime plus 3 root 15 over 15. So now the 15 cancels out and we just have x squared plus y prime plus 3 over root 15. So now we have a new quadratic function in terms of x prime and y prime, and there's no big difference between the coefficients. And that's going to lead to the Hessian not having a very large difference in the eigenvalues. Okay, so that's what this math is doing. So we define x prime and y prime according to these coefficients, according to the square root of the coefficients, and then so that when we simplify everything, we get a coefficient of 1. So now we can actually do gradient descent in the x prime and y prime coordinates, and then the convergence is very, very fast. So this is the idea of adaptive gradient methods. Sometimes the convergence is slow because the function is just kind of the shape of the function can become very nice if we scale the different directions in the right way, right? And this is kind of an example of scaling the different directions in the correct way. And then we get a very nice looking function. So in general, so that was just a very specific case, but in general, we want to transform our theta into some theta prime, right? So if we go back to the one note, when we define x prime equals 2x, y prime equals y over root 15, that's actually just the same thing as x prime y prime equals to a xy, where a is equal to 2, 0, 0, root 15. So in general, we can always define theta prime equals a theta for some a. Okay, if we do this, then of course theta will be a inverse theta prime. So our objective function used to be L of theta. So now that becomes, actually maybe doing it the other way is a little better. Sorry about that, just to be consistent with the slides. So actually we want to define we want to define theta prime to be a inverse theta, and then theta would be a theta prime. So now L of theta is the same as L of a inverse theta. Sorry. Yeah, so I'm confusing myself. This is actually, we're just plugging in theta here. So L of theta will be equal to a theta prime, like that. So now instead of taking the gradient of L of theta, right, we won't do that anymore. We're going to take the gradient with respect to the new variable that we defined of L of a theta prime. The objective can't change, of course. Okay, so that actually equals 2. So now we have to do the chain rule. We have to take the gradient of the outside. So the gradient of the outside is partial. So the gradient with respect to theta of L of a theta prime, and then that gets multiplied by the gradient with respect to theta prime of a theta prime. Okay, so that's the chain rule. So the first part is just the matrix derivative that we have seen before. So that gives us A transpose. The second part, right, the second part is actually nothing other, the second part, this part is just theta, right? So this is just the previous gradient before. So we just have A transpose the previous gradient. Okay, I guess I don't need to repeat that. So basically the new gradient in the new variable would be equal to some matrix times the previous gradient. And we can always invert it. So then the original gradient can be written as A transpose inverse of the other gradient that we just got. Okay. So previously, you can kind of see that when we take the gradient of this expression, it will just be A transpose. In this case, A is symmetric, so that doesn't matter. It will be A transpose times the original gradient. The original gradient had a very large magnitude in the x direction and a small magnitude in the y direction. When we multiply that gradient by this matrix, we have a much more balanced gradient that is kind of equal in every direction. In every direction in x prime and y prime. Okay, so that's kind of the general form of the general idea of adaptive gradient methods. So the main problem here is that in our previous function, we used our mathematical intuition to look at the coefficients, and then we figured out what A should be. In general, when you have a very complicated function, it may not be easy to figure out what A should be. So then that's where the adaptive part comes in. So we don't know what A should be, but we're going to continuously keep track of what A should be over time. Okay, so let me just present ADAGRAD, which is short for adaptive gradient. So let's do a comparison with gradient descent. So gradient descent, pretty simple. Here we just subtract step size times the gradient. Over here in the same line for ADAGRAD, we're going to subtract step size times D inverse, some matrix D inverse, times this gradient. So the idea of the D inverse is actually from the previous slide. We want to scale the gradient somehow using an inverse of a matrix in order to get a better direction for moving our parameters down. So now what is this direction? How can we compute D inverse? Well, D inverse is actually a diagonal matrix composed of this expression. Okay, so this looks a little bit messy, so let me unpack this. Okay, so for ADAGRAD, we want our D matrix to be diagonal of. So let me just repeat what's on the slides and then explain what this all means. Okay, I equals 1 to n. Okay, so this diag thing is basically like a short way of writing down a diagonal matrix. So for example, if I do diag of 1, 2, so that's equal to a matrix with a diagonal matrix with 1 and 2 on the diagonal. So over here, I have a diagonal matrix which is n by n. So that's what the I from 1 to n means. And in each of the element, I'm going to have the sum from the first iteration to the previous iteration of the partial derivative, the ith partial derivative, evaluated at the previous, evaluated at that particular parameter theta squared. So it's a little messy. And then square root. Right, so we're going to start from the very first iteration. We're going to compute the square of the gradient, of the first component of the gradient at that step. And then we're going to add that to the square of the gradient, of the first component of the gradient at the second time step. We're going to keep adding these squared gradient components up to the previous time step, or the previous iteration. Okay. And of course, we do this. For the second one, it will be the same thing, except that I is now equal to 2. So now everything here is going to involve the second component. So partial derivative with respect to theta 2. And then we square this and then square root all of that. Okay, and then 0 everywhere else. So what exactly does this mean? So we're always keeping track of how big our gradient component is for each component. If we had consistently big components, in each component, if we had consistently big gradients, then these values are going to be big, right? Because we're just adding the square of them. And then back on the slide, we're going to multiply our gradient by the inverse. So components with consistently big gradients will have their gradient scaled down proportionally. So that's what AdaGrad is doing. So going back to this example, in this direction, the component of the gradient is consistently large. So AdaGrad is going to scale over time. AdaGrad will scale the gradient in this component down. Whereas in the other direction, we consistently have pretty small gradients. So AdaGrad will scale up these gradients. So that's actually exactly what we did by hand over here. We were scaling down in the x direction, and then we're scaling up in the y direction. It's just that in this example, because it's so simple, we could analytically determine what's the best way to rescale the different directions. But in AdaGrad, we do that adaptively by keeping track of historically in the previous iterations, which component of the gradient has been large and which components of the gradient have been small. Right? So again, this diagonal matrix looks a little ugly, but that's what it means. Okay, so that's AdaGrad. So maybe some of you have seen this in somewhere. Maybe if you're playing with some machine learning packages like PyTorch, you may have seen this option. So the cool thing here is that as the function shape changes, so sometimes the functions, even this function, I would say is a very nice function because the gradient magnitudes are pretty consistent in the two directions. But some functions could be really strange, have some really strange shapes. After many iterations, sometimes perhaps a different component ends up having large gradients, and then some other component which used to have large gradients now have small gradients. So basically AdaGrad is keeping track of the history of the gradient size and then scaling things up or down to counteract the historical gradient sizes. Okay, so that's adequate. So this D matrix is called the preconditioner. Preconditioners are basically something we multiply the gradient by to rescale the different components of the gradient. Okay, next we have ADAM. ADAM actually stands for Adaptive Moment Estimation. This is actually, this is basically ADAGRAD with momentum. Or you could think of it as momentum with adaptive gradients. Okay, so this looks a little ugly. So we're gonna go through it slowly again. So let's see. Let's start with this line over here. So this line looks kind of like momentum because we have theta t. It's gonna become theta t minus 1 times step size. This thing inverse. This inverse thing is gonna be the same as this d inverse, and then times something with momentum here. The m stands for momentum, and it's basically, it kind of looks like the momentum line here when we calculate the velocity. So here we have m. M, think of that as delta theta. So delta theta becomes alpha times delta theta minus 1 minus alpha, the gradient. So here, instead of some step size, we're just going to say that the step size is 1 minus alpha. Okay, when you combine this expression with the 1 minus alpha t over here, that actually gives you something that is somehow normalized. Because if you plug this whole thing in here, you will get alpha over 1 minus alpha for the first coefficient, and then 1 minus alpha over 1 minus alpha t for the second coefficient. So then basically we still get to choose our step size based on alpha t here, indirectly somewhat. Okay, so maybe I'll write this down as well. So ADAM. So ADAM basically has, so let's write down the m part first. So this just looks like momentum. And then theta, the next theta will be previous theta plus gamma t, and then something inverse, which I'm not going to bother copying. And then 1 minus alpha t. So this alpha t could be different from the alpha up here. This alpha t is something that we can choose, another hyperparameter that we can choose. So now if I just wanted to make sure this is completely clear. Yeah, so that's not plus. Oh, that should be minus. Gamma t and then preconditioner inverse. And then if we just plug in what m actually is, we'll get alpha minus alpha over 1 minus alpha t, the previous m. So if we want, we can even put an mt here, the current m, right? Just to make everything really clear. The previous m plus 1 minus alpha over 1 minus alpha t times the gradient at the previous iteration. So that's what the entire expression looks like. So this part is basically something that is hopefully close to being between 1 and 0, between 0 and 1, just like the momentum. And then this part is basically just the gradient. Okay, so basically we just have the same thing as momentum so far, plus the preconditioner. It's just that the way we write things is a little bit different, but the idea is the same, right? We have we have this velocity thing that gets updated based on a gradient. And then the velocity term is now coming, the gradient is now the acceleration. The velocity term is now in the update for the position theta. So now we just have this term in front, 1 over 1 minus alpha t, and that's just the way people write it. It's a bit clearer. This is kind of like related to the step size. Okay, but if we combine these two lines, hopefully you'll see the similarity to momentum. So now let's take a look at this preconditioner. So the preconditioner, we're gonna take the inverse of it. So some of it is actually not a big deal. For example, this plus epsilon I is just to make sure that if this part is very close to 0, we're not taking the inverse of something that is very close to 0. The plus epsilon I makes sure that the inverse can be taken. So this is actually pretty similar to a lot of in many other algorithms in computer science. When we divide by a number that could be close to 0, sometimes we may just add epsilon to the denominator just to make sure that we're not really dividing by 0. Okay, so that's what this epsilon I is. So now let's take a look at the 1 minus beta d. And then d is this thing. Okay, so yeah, let's write it down again. Okay, so we're now going to focus on this part. And this part is basically, we have this plus epsilon I, which we're not going to talk about that much. But this part is 1 over 1 minus beta t d to the 1/2, where d is obtained from the previous d times beta plus 1 minus beta. So this is kind of like a weighted average of the diagonal of our gradient components. Just making sure I get everything correct. And we need a square here as well. Okay, and this is the diagonal is from I equal 1 to n. So basically, we're going to construct this diagonal matrix over here. We're gonna take 1 minus beta for that one, average it with the previous d. So this is basically the expression for the exponential average of all the d's from the beginning. So you can kind of verify this, right? We take a little bit of the previous d and then add on top the new part, the new information about the gradient components, and that gives us a d. This d basically involves a bunch of squares because the previous d had the previous gradient squared, and then every time we're adding a little bit of the next gradient squared. So this whole thing, think of it as a bunch of squared gradients. Previously with AdaGrad, we had the squared gradients and then square root the whole thing. So now we basically have this d is actually the squared of all the gradients previously. So that's why we had this square root over here. Okay, and then again, we just write previously. Yeah, maybe back to the slides now. Previously with AdaGrad, we simply had a step size parameter here. And then for Atom, we have the beta 1 minus beta, and then we divide by 1 minus beta t over here. So that's basically kind of like what is the weight on d over here, just to keep things close to 1, basically. Keep beta over 1 minus beta t, and then 1 minus beta over 1 minus beta t. Keep all of those coefficients close to 1. And then everything gets inverted and then multiplied by the step size outside here. So Atom actually has quite a few different hyperparameters. Okay, so Atom looks a little bit complicated on the slide when we write things down in math. But in the assignment, you'll get to implement Atom by hand, and then that will give you a better idea of it will give you a better idea of how Atom actually works. In code, it's actually pretty simple. So both AtterGrad and Atom are doing preconditioning. It's scaling the gradient somehow. But the way that the gradient gets scaled is by some diagonal matrix. So D is the diagonal matrix, and then when you take the square root of every diagonal component, invert, you're still gonna get a diagonal matrix, right? So the scaling is always in the same directions as the different axes. But sometimes that may not be the right thing to do. So all the previous methods used a diagonal preconditioner, right? That means that the A matrix that we saw a while ago, when we kind of motivated conditioning, so this A matrix, for Atom and AtterGrad, A is always diagonal. But sometimes maybe that's not what we want. In general, we may want some other transformation, A inverse, to take us from theta to theta prime. In that case, and sometimes A inverse may not be diagonal, right? Sometimes our function is somehow rotated, is not really, think of a paraboloid that is not axis aligned. It's kind of like a rotated parabola. So in this case, maybe it doesn't make sense to use a diagonal preconditioner. So maybe you want to actually scale the function in the off-axis directions. Okay, just to demonstrate this, I'm just going to create an objective function by hand, just to make sure that we're simply going to rotate this paraboloid by 45 degrees. So in assignment 1, you have seen the rotation matrix. So we're going to rotate all the xy's by 45 degrees. And then, so I'm going to skip the math over here. If you do that and plug everything into f, you get the new f function. So this is 2x minus y squared plus x plus y plus 3 root 2 squared over 30. So this function is still a paraboloid, it's just rotated 45 degrees. However, a diagonal preconditioner wouldn't really be able to make all the coefficients 1 simply by scaling x and y individually. That means that we need to somehow scale diagonally. Of course, this is just a very simple example. In general, how do you do the scaling for any arbitrary function? So this is what Newton's method is doing. It's going to use the inverse Hessian as the preconditioner. So Newton's method is known as a second order optimization method because it uses the Hessian. All the previous methods, they only use the gradient, which is a first order derivative. Newton's method used the Hessian, which is kind of like a second order derivative, or maybe coming from the second order Taylor expansion. So it's a second order method. Let's compare Newton's method with gradient descent. So gradient descent, again, pretty simple. Simply take the previous parameter, subtract step size times gradient. Newton's method actually looks very much like AtterGrad. If we go back to AtterGrad, right? So this line at least is going to be previous parameter minus step size times preconditioner times gradient. For Newton's method, the preconditioner is going to be the Hessian of the function. Okay, so it turns out that this is, we can show, so we're not going to do it this class, but it's possible to show that this is the best, if you use second order information, this is actually the best preconditioner. Okay, so the benefit of Newton's method is that it will work just as well, no matter how you scale or rotate rotate the function. Newton's method will always rescale everything correctly so that gradient descent or the descent direction is always kind of properly scaled according to the different directions. We can actually show that if we initialize close enough to a local minimum, then Newton's method will converge very, very quickly at a quadratic rate. So the meaning of the quadratic rate is that the gap between the local minimum and the objective value is decreasing at a rate of e to the power of minus e to the t. So this is actually much faster than even exponential convergence. Exponential convergence is actually big O of e to the minus t. But instead of a minus t here, we actually have minus e to the t. So it's actually extremely fast convergence. We can compare that to the previous gradient descent convergence rate. So here so epsilon is actually t. So previously it was more like 1 over t squared iterations needed. Actually, the gap is what we're looking at. So previously the gap was big theta of 1 over root t, right? So that's actually just the same as t to the power of minus 1/2. So it's a kind of a polynomial convergence, and it's a very slow polynomial convergence. For Newton's method, this is even much faster than even exponential convergence. Okay, so that's the benefits. The drawbacks. The drawbacks is that actually sometimes, yes, so sometimes if you initialize far away from the minimum, you may actually end up maximizing the objective instead of minimizing. And that's because of the inverse Hessian. If the Hessian is negative definite, we will actually move in the direction. We end up moving in the direction of the steepest ascent, not steepest descent. So when you initialize theta far away from a local minimum, if you initialize in a region where the Hessian has some negative eigenvalues, then the algorithm may actually diverge. Okay, there are some common tricks to this. Sometimes when we have negative eigenvalues in the Hessian, we may simply zero them out. We forcibly set all the negative eigenvalues to 0 in the Hessian and then take the inverse. So that means inverting only the positive eigenvalues. And then we can do this. So if you do that, it basically looks like Newton's method in some directions, but then it just looks like vanilla gradient descent in other directions. Okay, the other problem is that sometimes the Hessian may have very small eigenvalues, so that when you take the inverse will have very large eigenvalues, causing the update to blow up. Blow up means that this term, because Hessian inverse has some very large values, this whole term would have very large values. So then your next theta will change by a very large amount. So that's another issue with Newton's method. Okay, lastly, the Hessian is actually very expensive to compute because the number of entries is actually quadratic in the dimension of the parameter vector. If you have 10 components in the parameter, then H would be 10 by 10. It has 100 parameters, 100 entries. If you have, let's say, 1 million parameters, then H would have 1 million squared entries. So sometimes it becomes intractable to compute the inverse. Okay, so we talked about many different optimization algorithms. Let's just take a look at some of them. So we have SGD, so that's kind of like gradient descent, momentum, Nesterov's accelerated gradient, Adagrad, and then some other ones that we didn't talk about, Ada delta and RMS prop. Okay, but the point here is not really to necessarily know everything, know about all of these at this point, but just to compare them. If you look at SGD, which is a variation of gradient descent, you can kind of see that it's just getting stuck in the middle and it never rolls down. Some other algorithms are oscillating quite a bit before coming down. So right now it looks like the yellow one at a delta is doing very well. But if you use a different objective function, let's say something that looks more like this, you can see that the different colors are now going down faster. So the bottom line is that there's no single best optimization algorithm. In fact, choosing an optimization algorithm can be a hyperparameter in itself, right? And of course, within the optimization algorithm, you have other hyperparameters as well. And which algorithm works the best depends on the objective function. Actually, recently, Professor Curley, the other instructor of CMPT 726, has done some research on learning to optimize. So basically try to discover new optimization algorithms directly using machine learning. So the idea there is to replace the update formula with a model, with a model. The model could be, let's say, a linear model or a neural network, for example. And then we can find the parameters of that model to make the optimization algorithm converge the fastest. So then we're basically learning the update formula from data. Okay, so I think this is a good place to stop. Before we end today, let's do a bit of review since we covered quite a bit. So which of the following optimization algorithms uses a non-diagonal preconditioner? So why don't we take 2 minutes to think about this, and then before the end of the class, I'll go over the answers. Okay, let's take a look. So which one has a non-diagonal conditioner? So gradient descent, no. So gradient descent actually doesn't have a preconditioner. Okay, next, gradient descent with momentum. So actually that's just adding momentum to gradient descent, still no preconditioner. Nesterov's accelerated gradient. So that one, remember, was very similar to momentum, except that we're evaluating the gradient at the predicted next parameter value. So it doesn't have a preconditioner. Okay, ADAGRAD. So ADAGRAD does have a preconditioner, but it's actually a diagonal preconditioner, as we have seen over here. And the next one was ADAM. So ADAM does have a preconditioner, but it's also a diagonal preconditioner. But then the question is asking for a non-diagonal preconditioner. So ADAGRAD and ADAM both no. And finally, Newton's method. So Newton's method does have a non-diagonal preconditioner. We just saw that the preconditioner is actually the inverse of the Hessian matrix. Again, there are some up and downsides for Newton's method, but it does not have it has a non-diagonal preconditioner. So yes. Okay, so that's all for today. I'll see you guys next time.